Let's start today's seminar. Today's speaker is Sungwoo from Enrico Fermi Institute and University of Chicago. Here to talk about.
Don't panic. I'll come back again. I just realized. Yeah, you can continue to introduce me. Oh wait, there's a frozen. Okay. Yes. Sorry.
We'll talk about coupling a cosmic string to a TQFT.
Okay. Thank you very much for the invitation again and the introduction. So yeah, today I want to share with you some of the story that I've been exploring in recent years, not years, but 1 year or so, about thinking about coupling a cosmic string to a topological field theory sector. But really, if you are familiar, what I'm doing here is to couple a local quantum field theory to a sector of TQFT and study the implications, but really in terms of some topological defect allowed by those local QFT, because it stands much explicitly about the presence of such coupling to the TQFT sector. Okay? Ongoing work with the postdoc at U Chicago, Daniel Brennan, and then Professor Liantal Wang. So in any part of my talk, please interrupt me and ask any questions, because the point is not to rush through entire slide I prepared, but just really to share why I'm excited about and hopefully you can get some lessons and interest about it. All right, so with that, let's get started. So symmetries, right? So we are doing particle physics, especially fundamental physics, and we know how important symmetry is. And I just go through a little bit about symmetry part, and then I'll move on to the main part of my talk. So we know that how important it is symmetry plays in the theoretical physics, including high energy physics, more formal field theories, string theory, condensed matter theory. So here I will just show you a very brief list of how symmetry has what the roles that played by symmetries in more mundane physics of particle physics. First of all, we know the standard model is organized in terms of these symmetries, gauge symmetries, but without knowing yet what will be the global structure of the symmetry group. And that's one of the questions. And people have started investigating the question about this. And also the strong coupling sector of the standard model is described in the IR in terms of hierarchy, which is dictated by this symmetry breaking pattern of global symmetries, right? And really the global symmetry, which is a real symmetry rather than the redundancy of the description, can be explicitly broken by some parameters of the theory, can be anomalous by having some, say, either ABG anomalies or can possibly have a two anomalies, can be gauged if it does not have any two anomalies, right? So, for example, we have learned a lot from the two anomaly matching, right? So, two anomalies are invariant under any continuous deformations of theory. In particular, it is invariant under RG fluid. So, we learned that the matching of the two anomalies in the QCD taught us that even in the IR effective field theory, we should have, for example, investigating a Witten term. And this taught us a lot about the hadron physics of QCD, including CP violation and the actual magnitude of the neutral pi and decay to the gamma. Also, whether the skyrmion possibly appearing in the hierarchy must be quantized as either boson or fermion, depending on the number of colors, and many others, right? So recent years, really 10 years or so, the notion of symmetry has gone through really explosive generalizations, right? The first kind of generalization is that we've been talking a lot about the ordinary symmetries in which symmetry operator really acts on the zero-dimensional object or particle or local operators. Right? That's why it's called the zero form. But then we can start thinking a lot about the higher form symmetries, where now the charged objects are extended objects. For example, for one form symmetry, the charged object is the line operators, like Wilson line operators. And for two form symmetry, the charged object is a two-dimensional object called the surface operators. And I will talk about these a lot today. Second kind of generalization we have experienced in recent years is that while in the context of ordinary symmetries, we've been talking mostly about the group, right, mathematical structure of a group. Now we start talking about slightly more generalized structures. For example, as I will talk about a little bit, there is a notion of a higher groups where symmetries of a different form degree mixes up together. And also, very recently, people start talking about the non-invertible symmetries, where now there is no notion of inverse operation for a given symmetry transformation. And I will also touch base on a little bit about this back too. And lastly, although in most of the cases we talk about symmetry acting everywhere in the space and time, but there has been notion of a subsystem symmetries where symmetries is conserved along some particular direction, but not everywhere, especially realized in topological phase called the fractals and so on. So anyway, so there has been enormous generalizations of notion of symmetry in recent years, and the question is what will be the physical implications of that, right? But before we get to that, we have learned already that the generalized global symmetries of these three types of generalizations really has shown to be extremely powerful in understanding the structure of QFT, especially phase structure of the quantum field theory, including many papers. But here, really, this is a short list, but just to illustrate that it is a very important concept. Today, as a particle phenomenologist, I would like to ask the following questions, right? So these generalized global symmetries are great and beautiful and very fancy. But the question is, are there generalized symmetries in 3+1 dimensional QFT that we live in, which is relevant for particle physics, for example? So I'm interested in whether this can actually have a physical impact. And if there's such a theory exists, then the next question is that can there be observable signals, especially in local observable signals, even in principle, right? Regardless of how difficult or easy it is to measure those, because of the generalized symmetries. And lastly, really, I think one of the big questions is whether generalized symmetry can play an important role in providing meaningful and novel solutions to the big problems in particle physics, like, to me, hierarchy problems, massive neutrinos, and so on and so forth, right? So today, I will focus on the first two questions and try to answer partial answer at least to these questions. And yet, I think there's good chance for good answers to the last question too, but I'm happy to have offline chat about this last thing, but today I will just focus on the first two. Okay, so regarding the first question, whether there is a theory which is very standard to us that enjoys generalized symmetries, here I will just use a very simple theory called axion-Maxwell theory based on axion couples to hep-ph, and that theory, and also its topological modifications, which I will explain what I mean by that, enjoys a lot of generalized symmetries. Then the question is whether such a theory, including topological modifications, can have observable signals, right? So here today I will talk about two cases. The first, I will couple axion-Maxwell theory to a Zn topological field theory, and I show that this coupling explicitly modifies the local quantum field theory, but not 4D Berg quantum field theory, but two-dimensional string Rorschach QFT. So it modifies the explicit local QFT, which will have its own observable constancies. The second category of the topological modification of this theory that I'll talk about is that I will gauge a discrete subgroup of action shift symmetry. And I will also explain this can also be viewed as a coupling original theory to a sector of a topological field theory as well. And this time I will show that instead, it's not modifying local QFT, but instead it modifies explicitly cosmic string spectrums. And therefore, if we can do a spectroscopy of cosmic strings, we will learn whether such a theory actually couples to some TQFT or not. Okay, so that's the basic plan. So here's the outline of my talk. So first I will review to you the basics of axion-Maxwell theory, especially I will review some of the generalized symmetries, including three groups that this theory enjoys. And then in the second part of the talk, I will talk about first TQFT-coupling, in which I will couple to the Zn TQFT through what I call axion portal. And I will talk about either universal observables and possible UV completions. You will see that it's an extremely mundane UV completion. Therefore, such effect can be really there. It's not very exotic theory. And then in the last part of the talk, I will go in onto the gauging discrete subgroup of action shift, and then I will discuss modification of cosmic string spectrum. Okay? So that's the plan. And again, I'm not rushing. I don't want to rush. So if you have any questions, any clarification you need, please just jump in and ask.
What is the TQFT?
Oh, it is the topological quantum field theory. So
what is that?
why is that? So it's what is it?
Yeah.
It is a quantum field theory, okay, which does not have a local degree of freedom, and any information about that QFT is completely independent of any metric information. In fact, it only cares about the topology of the theory, including space-time metric or field space topology and so on.
So you don't use the metric.
Yeah, as you will see, I will show a Lagrangian of a particular Z and TQFT. It doesn't know anything about the metric. And in fact, there is no local propagating degree of freedom. The only thing it has is the topological degree of freedom, which I will explain.
This because many of the audience are not familiar with this, I guess.
Okay.
Maybe other distinctions? Maybe you guys know of this. I don't think it's generally people know.
Right. So the kind of TQFT that I will use today is one of the simplest kind, which I will also explain to you what I mean by this. Okay, so here I'm not invoking very general or very fancy TQFT, but I will take one of the simplest possible, and I will indeed explain to you what is Z and TQFT, why it is Z and TQFT, and so on. So I will explain to you about that in a couple of slides. Okay, anyway, the meaning is a topological quantum field theory. So meaning it depends only on the topology.
Just to clarify that, what is the gauging missing here?
Right. So gauging means that let's say you have, for example, U1 global symmetry. You had the fermions, and then if the set of the fermions are in such a way that it doesn't have any 't anomaly, okay, then if it doesn't have an anomaly means that if you wish, you can gauge the symmetry to turn into from the global symmetry into gauge symmetry. Okay, so I will also discuss in more detail what I mean by actually gauging the symmetry. So yeah, I will also explain the difference among like ABJ anomalies, 't anomalies, and gauge anomalies, so that I can clarify what I mean by all these words. Any other questions before I move on to the first part of the talk? Okay, so let's move on. So axion-Maxwell theory. So this theory, I'm talking about this theory, right? So there's the axion, there's the U1A gauge sector, and then there's a coupling between axion and then FF tilde, as usual. Okay, so you have seen this theory before. So I will use form notation today because it simplifies a lot of writings. So in case you're not familiar, a wet product is in fact two forms. Like this is two form because it carries two indices, two form and two antisymmetric indices. And the wedge product is that you product the two objects with a complete antisymmetric manner. And whenever you see like wedge together with a star, you can just view this as having a Lorentz contraction. Like you have a contraction of indices. Okay, but practically that's what it is. There's a mathematical meaning, but that's all I need today. So I will use this theory. So there's the axion kinetic term, and then U1A gauge theory kinetic term. There's coupling. Okay, so this is a theory, and this theory enjoys a lot of generalized global symmetries. Let me just go through some of them. So first of all, there's a zero form shift symmetry. Remember, axion is a Goldstone boson. Goldstone boson comes from the shift symmetry, right, which is spontaneously broken. So that means that axion, this is a dimensionless combination of axion field theta. Theta can be shifted by some parameter c, which is S1 value, meaning it takes the S1 value. You can see the existence of this symmetry from the equations motion of the axion field, which is here's the equations of motion without this coupling for now. So let me just turn this up for a second. And then you can view this as a conservation of the current equation, right? You can view this as a conservation of current. So therefore this, with some proper factor, can be viewed as a current. So there's a symmetry, right? There's a conserved current, there's a symmetry. Now, this is a zero form because it acts on the axion, which is the local operator, and associated the current is a one form. And I'm just going to be using the dual form of that. So whenever you see dual, means that this turns into one form into three form, meaning 4 minus whatever that form degree. Okay, so star J1 is a three form object. Now, if I turn on this coupling between axion and the gauge field sector. This coupling breaks this U1 shift symmetry down to the ZK shift symmetry, where K is this coupling constant K. Okay, so I'm happy to explain several ways how to see that, but if you admit this fact, that's the fact. So this coupling breaks U1 zero form shift symmetry to ZK zero form symmetry. Now, you can rewrite this equation in terms of something which is not conserved, by moving this to the left-hand side and realizing that this FHF can be written as a derivative of the Son-Simons factor. And note that naively, this operation is ill-defined because Chern-Simons action is not invariant under arbitrary U1 transformation, but one can show that this is the gauge invariant under ZK transformation. That's why this current is well-defined and gauge invariant. Okay, so now you have the conserved current for the ZK zero-form symmetry. You can construct the charge by integrating that current over the three-dimensional manifold. Because this is free form, you can also define what's called the symmetry defect operator by exponentiating this charge. So now the way it works is that zero form means that there's a charged object, which is like point, axion. And then you can measure the charge of this object by wrapping this guy with this symmetry defect operator, which is defined like this. And whenever there's what's called non-trivial linking, meaning when you try to measure this, you're basically measuring the flux coming out of this guy, right? That measures charge of this object. Okay, this concept will be used quite often. So there's a zero-form action symmetry. There's a two-form action winding symmetry. This is a dual symmetry to the zero-form action symmetry. And this comes from the fact that the d square derivative is 0, right? D square is 0 in differential form. So that, again, you read this as if it is d times something is 0, and again, the current with the proper normalization is this one. So this is almost a topology trivial fact, but nonetheless, there is associated symmetry called the two-form U1 symmetry. Why two-form? Remember, for the zero form, there's a one-form current. So two-form means there's a three-form current, and I just dualized it. Okay, now this is the one-dimensional object. So then again, you can construct the current, the charge by integrating this one-form object over the one-dimensional manifold, and this object is nothing but winding number. So now this is a two-form U1 symmetry. Therefore, charged objects are two-dimensional object, which is called the two-dimensional causing string. Okay, so you can think of it as the very thin string in the space, and then there's a time in moving. Okay, that's two-dimensional world shape. So the charged object under this two-form symmetry is the causing string. And then it's measured. The charge of this two-dimensional object is measured by this charge operator, which is basically a winding number. Okay, so that's the two-form symmetry. There's also, moving on to the gauge theory sector, there's also one-form electric symmetry. Again, you can just get the equations of motion of this sector, forgetting about the coupling for a second, and that gives you this thing. And then again, you read this as if it is a derivative of a current equal to 0. So here it is a two-form, therefore it corresponds to a one-form electric symmetry. So one-form, that means that the charged object is a one-dimensional object. In fact, it is a Wilson line. And then again, if you turn on this coupling, it breaks this U1 electric symmetry down to the ZK one-form symmetry, similar to the zero-form action symmetry.
It was the previous slide. So here in the figure.
Yes.
Could you explain how charge operator act on the object?
Yeah, so it's a little bit non-trivial because we are in the 4 dimensions. Okay, so suppose, imagine that you live in the 3-dimensional world, like including time, you live in the 3-dimensional world. Okay, not 4, because I cannot visualize 4 dimensions, so 3D. So then one-form symmetry, so two-form symmetry. Oh, so that's a little bit subtle. So the better object is actually one-form electric symmetry with the Wilson line is better to. So okay, suppose now I learned the trick. Let's say we live in the 3D world. Okay, and suppose I have a trivial electromagnetic theory, ENF. Okay, then there's a Wilson line, one-dimensional object, which is either the I alpha just A. Okay, I'm just doing the 3D ENM. Okay, so this can be represented as line, Wilson line. Okay, now there is a U1 one-form electric symmetry, and one can show that whose symmetry defect operator is also integrating over the 1D. So let me just do N to denote the charge of that. So that's also alpha F star, which is along the 2D, but you see if you use the Stubbs theorem, this is a 1D object. So now you link the charge operator. This is a charge symmetry defect operator. This is the Wilson line. You see that there's a non-trivial linking, meaning this guy cannot escape out of this thing without cutting it, right? So this is how you measure charge of the some object from a symmetry defect operator. So you have to have a non-trivial linking, what is called. if you ask what is the general mathematical definition in 4 dimensions, there's such a thing. So first of all, in this picture, you first look at this surface and you count the crossing number, and then you can count that. But there's a mathematical generalization. It's just that in 4D, I cannot visualize this picture in a proper. That's why I just draw that way. But really, this is the concept.
I'm asking something simple. I think, for example, we know that the momentum operator is the generator of space translation, right?
Yes, sir.
So I'm asking, what's the role of this charge? What kind of motion it generates on the string?
Right. So it's not generating the motion. It measures just like if you had an electromagnetic charge operator, and then there's a point charged particle. You wrap that with a 3-dimensional charge, right? And then what it measures is that it measures the electric flux, and therefore it tells you that the charge should be something. Same here. This charge operator, you wrap this charged object, but then the charge in this case is the winding number. So therefore, this charge operator measures the winding number, which is nothing but the charge of this cosmic string object. So that there's a point particle, there's a charge, there's a cosmic string, there's a winding number. That's the correspondence.
And is there any notion of global symmetry and local symmetry?
So these are, so far I'm talking about all global symmetries, generalized global symmetries. Everything is global symmetry. I haven't gauged yet.
Okay, I'll ask you later.
Okay. Yeah, okay. So again, now I'm talking about U1 one form electric symmetry. So here again, this topological coupling will break this U1 one form symmetry down to the ZK one form symmetry. Again, you can show, but again, looking at this word identity, you can rewrite this in terms of something total divergent term by moving this guy on this side and then basically redefine the term to be this. Anyway, this is technical detail. And then once you have this current, you can again define the symmetric defect operator, and you can measure the charge of, in this case, charged object, which is Wilson line. Okay? And there's also dual symmetry to this one form electric symmetry, which comes from the Bianchi identity of this U1A KC receptor. This is it. And then you read off this as again conservation of the current. Here, current is basically proportional to the field strength. Okay. This is U1 magnetic one form symmetry, and nothing breaks it, so it survives as a good U1 symmetry. Here, charged object is the dual of the Wilson line, which is a two line, and so you integrate over the dual gauge field. So that's the picture. So anyway, so there's individually there are 4 symmetries enjoyed by this theory, but they form what's called the 3 group. Okay. So in order to see that, I first rewrite this term in terms of that, which is the equivalent term. In fact, not.
Before you go ahead, the introduction, you said you are going to talk about topological conductivity.
Yeah.
So it's sincerely without defined in terms of symmetry.
Yeah.
So I guess you have to keep only the last one.
No, I haven't talked about TQFT yet.
Okay.
I'm talking about axion-Maxwell theory just now, and then I'll couple this guy to the TQFT sector. That's the goal. Let's see how it goes. So first, I rewrite this in terms of in 5-dimensional manifold, okay, such that this is equivalent to that. There's a little bit of something going behind this in order to define the theory well defined everywhere, including a cosmic string core. But for now, let me just skip through the details. But anyway, this you can just believe me equivalent to this, up to some technical details. Now, I can couple this theory to background gauge field of global symmetries. So I reviewed to you 4 global symmetries, right? So I can couple this theory to its background gauge field. So if I do that, it looks like this. So this looks like complicated. So let me just point to one thing and show that I'm not lying to you. So look at this. So if you had a global symmetry, you can couple that to the source field A mu, right? This is a background gauge field. So just like that, I can do the same thing. Remember, for axion shift symmetry, the current is proportional to this factor, star dA. And indeed, I coupled to its background gauge field A1, but in a manifestly invariant way. Here too, I said that there is a U1 or ZK one form electric symmetry, which is current is this, and then I coupled its background gauge field. And basically, I did everything in a very consistent way. Now, 3 form arises by the fact that this axion, especially the last stuff, which I write in the 5-dimensional manifold, whose boundary is a space-time manifold must be independent of a choice of n5, because this is auxiliary choice, right? So imposing that choice gives me the fact that these two factors, which you can think of it as the field strengths of the magnetic symmetries, like two-form magnetic symmetry, one-form magnetic symmetry, cannot be just naive derivative of its own background gauge. It should be modified, including extra terms. Otherwise, this actually is not independent of choice of n phi. Okay? So therefore, you see this equation. Now, one can derive a line by it. Anyway, so if you trust me, this field strength of a two-form magnetic symmetry and field strength of a one-form magnetic symmetry is not just naive its own derivative of its own gauge field, background gauge field, but it must have extra terms. So now let's actually understand the physics of this thing. So naively, I would have thought that it should be just that or that. Why do I have this? Again, I explain to you why. Now, the meaning of this thing is that now if you had a set of one-form electric flux, it can fuse to generate two-form winding symmetry. And this equation tells you that not only this, but also if you had a fuse of one-form electric symmetry background field and zero-form shift symmetry background, that it can fuse to generate one-form magnetic symmetry. In other words, there's a mixing, non-trivial mixing among different symmetries. And this phenomena is called the higher group. In this case, it's called the three group because the amount of mixing is done from 0, 1, 2-form symmetry. Especially the highest rank symmetry is 2-form. It's called the three group. Anyways, so there is that structure. But the point is that this theory, even though it looks like a very simple and mundane, enjoys a very large set of generalized symmetries. And very recently, like a couple of weeks ago, people pointed out that this theory also has what's called a non-invertible symmetry. I have a backup slide, but for now, let's just move on so that I can get to the point that I want to talk about. Okay? All right, so now let me couple this theory to Z and TQFT. Okay, any questions before I move on? Good, let's jump in. So again, here is the theory that I explained to you already. Now, I view this theory, which let me just relabel a little bit because I want to call this sector A sector. I just gave a subscript A everywhere. There is the original theory here. And then I want to couple to Z and TQFT sector, which has the two topological degree of freedom, which I will explain now. So that theory looks like this. So first of all, there is an action describing Z and TQFT, which would be a theory, which I will describe now. And then there is two terms that describing coupling between these two sectors. So let me first talk about these red terms. So there's axion and A1 term, which has the field strength FA. But this term describes the coupling between axion times field strength of A coupled to field strength of B, which is a derivative of B1. And this last term describes axia, which belongs to this sector, couples to f(h) f of this term. So this certainly describes the coupling between the two sectors, manifest to the local. Okay. Now let me get to this point. Why this describes the Z and TQFT? Again, the claim is that this describes the discrete gauge theory. If you look at it, so now this is topological field theory because first of all, this doesn't know anything about the metric. This is only written in terms of forms and then just wedge product without having a Hodge dual. So this is manifestly independent of any metric. Second, I will show now that this theory doesn't have any local degree of freedom. So let me see how. So first of all, why this describes the Z gauge theory? Because I can get it from Abel and Hicks model. So here is Abel and Hicks model. I had a U1B theory, and then I had the Hicks charged under U1B with a charge N, right? So if you had a U1B, Hicks down to the something with a charge N, obviously the leftover must be Zn, right? Gauge the Zn. However, if you look at these two terms, for example, there's a star d phi times NB1. So let me just now dualize d phi into B2, meaning this is a one form. If I dualize, it becomes three forms. It becomes derivative of two form. Now this starts looking like this action that I wrote here. Indeed, you can show explicitly that this theory is equivalent to this term up to some terms that they will be covered pretty soon. So indeed, I know that physically this action describes the Z-gauge theory because it comes from the Abel and Hicks model, which manifestly describes the Z-gauge theory DIR. Okay, this is topological because if you look at the equations of motion of these two fields, this is the answer. This is the equation of motion. So obviously, this is trivial constraint equation, right? There's no two derivative term. In order to have a propagating mode, you need to have a two derivative in the equations of motion, right? That's why you have 1 over p squared. Start propagating. So this doesn't have a propagating degree of freedom. Nonetheless, this theory is not trivial because these two, first of all, there is a non-trivial gauge invariant operators. There's Wilson line operator integrating the B1 over line. There is a Wilson surface operator integrating B2 over surface. There are gauge invariant Wilson operators. So it's not empty theory. And in addition to that, these operators satisfy non-trivial correlation functions. Or they satisfy non-trivial braiding. So therefore, this describes non-trivial structure. In particular, it actually describes non-trivial vacuum structure and associated selection rules. You have a question? Okay. Okay, so this is the gauge theory. Now let me go back to this theory. So now I explain to you why this is described as Zn TQFT, and this corresponds to coupling between this sector, visible sector, and TQFT. So here really the question is, now can there be a universal local observable effect because of this coupling? Okay. And the second question is whether this action can be obtained from rather standard QFT, or is it very exotic or academic setup? So that's the question. And I will show you soon that this can be obtained from pretty standard QFT. Therefore, at least one of the messages this delivers to me is that it is important now to study remnant TQFT couplings, because it is very easy to leak out this effect, yet we might be missing such effect if we don't actually keep track of those effects carefully. Okay? So with that, let me move on to the next part of the talk. I will discuss these two parts one by one. Okay, any questions so far? Okay.
Sorry.
Yeah.
So you, in the beginning, you started the axion coupled to electromagnetic.
Yeah.
Now you are studying the axion coupled to
Coupled to this Zn gauge theory section. What's called the Zn TQFT.
First line, you have, now I lost my glass. So
Okay, this is the original axion-Maxwell theory.
so the first line.
Yes. The second line has the first term is the action for the BF theory, the Zn TQFT itself. So this describes this sector alone. And the two red terms
And
describe
sorry, B1 and B2 are independent.
B1, B2 are independent.
Yeah.
Yes.
One form, two form.
Yes, one form, two form.
And then the FAFB.
Yeah, these two terms, which looks pretty much like this, but in such a way that at least the one of the factor includes degree of freedom, in this case, topological degree of freedom from the BF theory sector. So this describes the coupling, local coupling between the axion-Maxwell and then Zn TQFT.
So FP is a build strand of
B1, yes. So this BB1 is a FP. Sorry. Yes.
Then, so you can also consider DB2.
That's a three form. Indeed, it's there, but if this theory comes from the Abel and Hicks model as the way I described, it will pretty quickly decouple. So it will just go away and then it will decouple. But in principle, yeah, one can consider that too. Okay, so universal observables. Okay, so and then the theoretical tool to analyze this effect is anomaly inflow. Okay, so let's just quickly review to you anomaly inflow without a TQFT coupling. So this is original theory, right? Without a coupling to the TQFT sector. And suppose in the space, so now you imagine there's a space, there is a whole bunch of cosmic strings like this coming from this here. This is axion strings. Now let me zoom in one of the string, and then denote this picture in terms of this blown up picture like this. Okay, again, this entire picture is nothing but this cosmic string. And as we talked about, this cosmic string is a two-dimensional object and charged under two-form symmetry, whose charge operator is a winding number of axion. So suppose I have one cosmic string with a winding number 1. So that's the setup. Now, this theory is a gauge theory, right? There's a U1A unbroken gauge symmetry. So that means that this theory should be manifestly invariant under U1 gauge transformation. But however, this term, which I just rewrite in this way, is not invariant under this gauge transformation. In fact, one can show that under this transformation, this changes by this term. So let me explain the expression of this meaning of this expression. This term changes to this, and there is a delta function or generalization of delta function, which basically is saying that this is 0 everywhere except string core. Okay, cosine string core. And then the size of the violation of the gauge symmetry is f over 4 pi times some number. And f over 4 pi, just remind you that is the consistent anomaly in two-dimensional TQFT. So let me just discuss again what I have just done that. So there's a violation of the U1 gauge invariance naively from this theory, but that is localized completely on the cosine string core, which can also be viewed from the divergence of the current too. So in order to restore the consistency of theory, meaning everything is gauge invariant, that means that there must be a localized 2D QFT here, which is also anomalous, gauge anomalous. It must have, therefore, its own gauge anomaly. And in together, right, there is a gauge anomaly from the work, there's a gauge anomaly from the 2D QFT. They cancel out together to form a consistent theory. So what do I need for the 2D QFT living here? The requirement is that since I have this anomaly from outside, so here I'm just explaining to you the same physics, again, anomaly inflow, but in terms of current. So let me just rewrite this topological current in terms of gauge coupling times the current, right? I can just view that way. And then current, you can obtain by taking the function of derivative with respect to A1, so that's the answer. Okay, and then we have talked about a lot that the divergence of this thing is not 0, but there is an anomaly localized in the cosine string. Okay. Now, this thing from this expression, you can read out the vectorial part of the current, which looks like the divergence gradient of the axion times electric field. So there's the electric field, there's the gradient of that. Okay, and this is called the whole line current because current is not parallel to the external source of electric field, but actually it's a perpendicular to them. Okay, so this phenomenon is the whole line current. Good. So now what happened is if my cosmic string passes through background electric field, which is in this picture is negative z direction, due to this fact, it will trigger a current which is marching towards the core of the axion string. Now, if there's a notion of current conservation, somehow this should go into somewhere, right? Otherwise, there is an abrupt stop of current. That means that there must be a current flowing through the cosmic string. And this thing is nothing but current made out of a 2D chiral fermion living on the cosmic string core. And those are two-dimensional degree of freedom described in 2D QFT of the cosmic string. And it must have its own two-dimensional gauge anomaly in such a way that the size and sign is opposite to the work anomaly to cancel this out. Okay, so that's the picture. So now let me generalize this anomaly inflow when we do have TQFT couplings. That's a simple generalization of analysis. Now, if you vary this action with respect to U1A gauge transformation, so there's a U1A here, U1A here. So you get a two non-invariants from here. So one from here, the other from there. Again, localized on the cosmic string core. You can also vary this action with respect to now Zn gauge transformation. So here, gauge parameter is Zn valued, as you see here. Again, there's a B1 here, and there's a B1 here. So you get two terms. Okay, again, localized on the cosmic string core. So now let's study the meaning of this equation. So first, starting from the variation with respect to U1A transformation, right? So I'm varying with respect to U1A, and then I have U1A field strength there, right? So which means that this term describes the U1A squared to the anomaly, okay? Which means that, of course, the charge carrier along the cosmic string must be charged under U1A. But that's what it means. Now, if I turn on the coupling to the TQFT sector, this tells me that under the variation of U1A, I must have U1B, or more precisely, ZNB anomaly. So that there is a mixed anomaly, which means that now my charge carrier along the cosmic string must also be charged under Zn as well as U1B. So I'm explicitly modifying the 2D QFT structures, right? My charge carrier is not enough to be charged under only U1A, but it also must be charged under Zn gauge force. Okay, let me finish. So in the current picture, therefore, in terms of physics of the cosmic string, if my cosmic string passes through the background field of the electric field, because I'm there with respect to electric V, then the first anomaly tells me there should be a charge carrier, which carries the U1A quantum number. But the second mixed anomaly tells me that that must also carry Zn charges. So therefore, the nature of the superconducting current along the cosmic string has modified.
Can I ask a basic question?
Yeah.
In the previous slide.
Yes.
So everything is in function as a function of FA, right?
Yes. How is it even? Yeah, very good. So I'm glad you asked. That's actually an important question, right? Otherwise, it's very confusing. What do you mean by there is a non-invariance, right? So that action, so that's the technical part I said. So this action is not well defined everywhere. Remember, the correct dynamical variable is dA. And dA is not well defined in the presence of cosmic string core. Because if I just shrink dA, at some point there's a singularity. So really the action, which is well defined everywhere in the S4, is therefore looks like some K, 1 plus rho. I will explain what I mean by that, dA, A1, F2. So what I have done here is that first I did integration by part, that action, and then I inserted what's called the bump function. So this is a function of a radius. So there's a cosmic string. So this goes to 0 as r goes to 0. So therefore it turns off this entire term. So it makes it consistent before you hit the singularity. But this goes to 0 as r goes to infinity. So that means outside of the cosmic string, you return to the original action. So now if you vary this action, you actually get the variance that I showed. But that's important. Okay, so I told you the nature of current got modified. Moving on to the variation with respect to B, Zn symmetry. Again, the first term describes mixed anomaly because there's a Znb versus U1a. So there's a mixed anomaly. And this term describes the Zn squared to the anomaly. Okay? Again, similar to the previous thing, if my cosmic string now passes through Zn background somehow, let's say I look at the sky and there's no any electromagnetic activity at all. But then if my cosmic string passes through Zn somehow background, which you can imagine can be documented, which is our application soon, then it will trigger by anomaly inflow physics the current, which is not only Zn current, but simultaneously that it should also be U1 ENN current. So all of a sudden from the sky, dark sky, where there's absolutely no ENN activities, all of a sudden you might see a light because of this phenomena. Anyways, that's the application. But here the point is that the coupling to the TQFT sector explicitly modifies the nature of 2D QFT, leaving the cosmic string. So that's the summary. So without a TQFT, this is the picture. With TQFT, first you triple the amount of consistency check you have to make. And because of that, A, you modify the nature of the superconducting current. B, there's an extra mechanism to turn on that's such as superconducting current. Okay? So that's the first part of the talk. Let me quickly touch upon the second part. So hopefully I convinced you that if I couple a TQFT coupling, A, there's a modification of 2D string worksheet TQFT, and there's a different nature of a superconducting current, meaning it carries also Zn charges. There's new mechanism to turn on those superconducting currents. Now, these non-trivial TQFT coupling, the claim is they can arise from the very standard UV QFT, and if that's possible or that's true, then this really delivers a message that it is important to figure out remnant TQFT effect. Right here, I just show you that the TQFT can actually do something in terms of local observables, right? And if so, then it is important to incorporate this effect on the phenomenology study. So let me actually move on to the standard case. So what is the UV completion of the TQFT coupling I just described earlier? So let me first start with the standard case VZ. So this is the UV theory, which flows in the IR to the axion-Maxwell theory, right, without a TQFT coupling. So in the UV, there's a U1A gauge theory sector. And then there's a two fermion I call psi1 and chi1. And they carry vector-like charge under U1A. Because it's a gauge symmetry, I better not have any gauge anomaly. So it's vector-like, +1, -1. And then I want to be able to integrate this fermion. So I write down the Yukawa coupling, eventually giving a mass to the fermions. Now, since I have two fermions, I started with a 2U1 symmetry. One direction is anomaly free, which is gauged by this. The other direction is anomalous, which I chose to be along the psi1 direction. Now, this Yukawa coupling then tells me that since psi1 carries a charge 1 under global symmetry, this scalar phi also must carry charge 1 too, right? Otherwise, I cannot even write down this Yukawa coupling. Now, let's try to integrate the fermion. But before we do that, we have to do one job, because this scalar field, which now carry charge 1 under global symmetry, has a angular physical degrees of freedom, otherwise called axion. Right? So this term has the axion in addition to the mass term. So I want to rotate away this angular degree of freedom out of the Yukawa term, which I can do that by using this U1 psi1 rotations. Right? So I can just make this rotation, rotate away this axion degree of freedom. Okay. However, this rotation is anomalous, right? As I said, this is anomalous rotation. There's a U1 Patrick Quinn, U1A square ABJ anomaly. That means that if I do this transformation, it will turn on this topological coupling between axion and then hep-ph. So once I add this term to the action, now anyway, axion is out of the Yukawa coupling. This now turns into completely only the mass term. I can now integrate the fermion. And if I do that, I get to this axion-Maxwell here. That's the KSV. Okay, so let me do the same thing for our theory. So here is the same theory, but I want to have Zn in the IR, right? That's the goal. That means I started with the U1B gauge symmetry, and then I want to Higgs that down to the Zn by having a scalar having a charge n. So that's the starting point. That's the starting point. And because of the Yukawa coupling, I have to assign proper charges for fermion such that this thing is U1B invariant. That's why I've done that. Good. But now I have a problem because this fermion is not anomaly free set under the U1B. In fact, there's a whole plethora of gauge anomalies. So I need to cancel these gauge anomalies by introducing a second set of the fermions. So you can check that this now cancels entire anomalies. But now I want to be able to integrate out this guy too, because in the IR, I don't have the fermions, right? So that means I want to be able to write down the second scalar that couples to the second set of the fermion to give it the mass. So that's the scalar by 2. But then because of the charge consideration, this thing must carry charge n on the U1.
What is the fermion mass in your?
They are of the order of the bed size of the scalars. You're asking the fermion mass.
Yeah, because you say you are integrating them out.
Yeah.
But I don't see the mass term.
So this Yukawa term will turn into the mass term once these guys get a bed.
Two gets a bed.
Yeah, both will get a bed. So I designed the potential such that they get a bed.
Yeah.
Okay, good. Now let me do the same procedure. Now I need to rotate away again angular parameter, angular degree of freedom of both phi 1 and phi 2 from the Yukawa by again doing rotations in terms of fermions. So here I'm using the psi 1 rotation. Here I'm using chi 2 rotation. But both are anomalous. Again, ABJ anomaly. So because of that, it will induce this anomalous term. But now you start seeing something, right? So there is not only FA wedge FA, there is ABBB terms with the proper anomaly coefficient. Now this particular linear combination of two angular degrees of freedom is to be identified as axion. Okay? And if you do that, now you can integrate the fermion, you get to this action. So here the point is not details of the construction, but it's pretty, to my mind, it's pretty modest extension of minimum case VZ, right? But it's just that I had the round of the Zn effect just because the scalars in UV had non-trivial charges. So this is where you can generate the Zn effect, and you need to keep track of those effects carefully in order to get the right phenomenology. Otherwise, you will miss all those effects I discussed.
So how this there can be the topological, I mean the B field, I mean in your UV completion.
So good. Your question is that how do I get the BF theory out of this thing? Is that your question?
Not just from in your UV completion.
Yeah.
The B field looks like just dynamical, right?
That's right. Why it turns into the topological degree of freedom? Very good. So the answer to that question is that this sector, so there is a second scalar phi 2 charged under, let me go back to one slide, charged under U1B with the charge n. So one linear combination of these scalars basically describe the abelian Higgs model with the charge n. And if you remember, I wrote down that action before. Let me just quickly write it down for you. So one linear combination of phi 1, phi 2, if you look at it, some coefficient factor, it will describe this because they carry charge n, obviously. And then this turns into in over 2 pi b2 wedge b1, where in this case b2 is the dual of t phi, the angular degree. That's how you get the TQFT out of this mundane QFT. Okay.
So physically, what is the U1B in physical?
In the UV theory, it is one of the very mundane U1 gauge theory sector, just nothing more than that. So in this UV construction, U1B is really one of those U1B gauge theory sector, but it happened to be that the scalars, which Higgs is that U1B, had a charge n rather than charge 1. If it had a charge 1, it will completely break. There is no Zn.
I'm not asking mathematical thing, but the U1A, we can interpret it as a U1 electron.
Yeah, for example.
I'm asking what is U1B.
I'm imagining there's a U1 ENM sector coupled to some Zn sector, which is a BSM sector, right?
Okay.
So I'm getting that BSM Zn sector out of in UV, another U1 sector. That's the point.
And you have two form.
Two form.
Only one form here. Only one form here.
In this language, there's only one form, but two form is obtained when you dualize the angular degree of freedom of one of the scalar fields.
Then can you interpret that two form as a Karp-Ramon field or not?
It behaves like a, yes, Karp-Ramon field. I mean, in other words, effectively, what I mean by that is that if you integrate this theory, in addition to this, there is something like 8 pi squared lambda square dB2 wedge dB2 and so on. So there are some extra terms. But like I said, if the UV cutoff scale is pretty high, they will decouple, and effectively you are left with only TQFT sector. So in that sense, in that limit, this guy behaves like a two-form field of the kind called Ramon field.
Generally speaking, B2 is a two form, and if you have a string moving, then you have a worldsheet element.
Beautiful, exactly. So that's one of the points that I want to get later. So this B2, this is the, so let me call this BF theory sector. And there is a Wilson surface operator, which is nothing but, integrating this B2 field over, as you said, string worship. So this is nothing but BF string configuration. BF theory string configuration, which is one of the points that I want to get to in the next part of the talk. Any questions? Did I answer your question or? Okay. Okay, so good. So with that, let me actually skip this part for me, zero mode part, although it's pretty interesting part. Let me just get to the last part so that I can deliver at least another yet different message. So in this part, I want to gauge, which I will explain what I mean by gauging, discrete subgroup of axion symmetry. So let me just recall or remind you that there was a zero from axion shift symmetry of this kind. I talked about this, right? And I said that from equations of motion, you can get this, but the topological coupling will break this down to the ZK. Okay, so this is the part that I already talked about, but I'm just reviewing to you. Now, this means that the ZK subgroup of the U1 shift symmetry is ABJ anomaly free part. Okay, what I mean by that? So let me also explain to you. So remember the action at IK A pi square F A F with F type of term, right? And this is IR ramification of the fact that UV, there was a fermion, and then there's axion, there is a gauge field. So it comes from the anomaly diagram, right? So this represents the gauge, insertion of a two gauge part. A represents U1 global symmetry part. So this is nothing but U1 ABJ anomaly because one is the global symmetry, the other two, global symmetry. The other two is the gauge symmetry. So it's testing whether this global symmetry is a good quantum symmetry or not. And such an anomaly between global symmetry and the rest is the gauge symmetry is called ABJ anomaly, the Adler-Bell-Jacob anomaly. If everything is global, that is called the 't Hooft anomaly. If everything is the gauge, it's called the gauge anomaly. Okay? So ABJ anomaly is what's testing a given global symmetry being whether good symmetry or not. Now, I'm telling you that this thing is invariant, completely invariant under if I shift axion only under ZK, which means that under ZK subgroup, okay, you don't have any ABJ anomaly, which means that that is a good quantum symmetry. Okay? So the point here is that this ZK is the anomaly, ABJ anomaly free part. So if I want to, I can gauge it because now it's a good quantum symmetry. But the question is what happens if I gauge this one? Okay, meaning I turn that into actually gauge symmetry now instead of global symmetry. But that may sound pretty exotic. So let me just explain to you that this gauging a subgroup can also be interpreted as a coupling to the TQFT. So how do I see that? So let me start with the mundane setup. So here is the global continuous symmetry, first of all, coupled to the background gauge field. So it's background gauge field. I had a sector which had a global current, global symmetric current, and I just coupled the background gauge field like that. Okay. Now let me decide to gauge this symmetry because say this doesn't have any ABJ anomaly. Then all of a sudden I have to have its own gauge theory sector. So I gauged it. And now all of a sudden this coupling between the current and gauge boson, the gauge field, describes the coupling between the two sectors. Right? So the gauging therefore generates picture of now coupling to some gauge theory sector. So I can, if I can repeat the same thing, here's my theory with the axion shift symmetry part. Remember, this star dA is the current for the action shift, and I couple to the background gauge field. Right? Again, there's this action theory. I couple to the background gauge field, which I call curly A1. Now, if I gauge Zn subgroup of this guy, then that will turn into, again, first of all, I must have a Zm BF theory sector because it is a Zm sector. And now this coupling between the current and the background gauge field now describes actual coupling between axion sector and the dynamical, by dynamical I mean a gauged field. Okay, so therefore, gauging is nothing but generating this picture of like having an axion theory sector coupled to, again, Zm TQFT, but now different Zm TQFT than the one that I discussed so far. So what is the physical implication of that? So let me just discuss to you one point. There are many points. There's many interesting features like this modifies the three group structures and so on and so forth. But here, let me just tell you one physical implications of this job. Is it clear that the gauging is same as coupling to another gauge theory sector through this picture? Hopefully. Okay. All right, so here's the setup. So therefore, I started with the axion theory, and then of course, there's all other terms. I just drop in here, and then there is now a BF theory sector, right? Zn BF theory sector. Now let's talk a little bit in detail about the gauging. So first of all, this gauging is a zero form symmetry, gauging of a zero form symmetry, because that I'm gauging zero form action shift symmetry, right? More importantly, this corresponds to non-linearly realized discrete symmetry. So what do I mean by that? So recall that, for example, Higgs action for the Higgs looks like this, right? The linear sigma model, we have the derivative of the Higgs minus gauge field and Higgs as well to the square. Right? This is a linear sigma model. In non-linear sigma model, in terms of angular variable of this Higgs, it looks like this. There's no phi appearing after the gauge field. Okay? So then, of course, we start from here. And this corresponds to Higgs or spontaneously broken shift symmetry, not the linearized version. What I mean by that, therefore, is that when I decide to gauge this shift symmetry, that means that there must be already non-linearly realized shift symmetry. Otherwise, how can I even gauge it, right? There should be global symmetry in order for me to gauge it. Okay, so this has an important point. This has one important implication. So let me just describe to you. I'm almost there, so let me just slow down. So remember, there was this picture. So this is energy scale. And then there was a scale of a phi of a Patrick-Quinn in the previous KSVG structure. Below, I get axion-Maxwell theory. Above, I have the psi's and chi's and so on, right? And then here, of course, the scalar had roughly half times e to the I axion. Okay? So the web of this guy breaks the U1 rotation of the axion down to the non-linear realized symmetry. Okay? So what I mean by that is that in this scale, phi gets shifted by linear like that, but below scale of spontaneous symmetry breaking, the transformation becomes non-linear realized. That's what I mean. Okay. Now, what I'm trying to do is that take that theory, I'm trying to gauge subgroup of this thing. That's what I'm trying to do. Which means that that non-linearly realized symmetry must exist already. Otherwise, how can I even gauge it at that time? Right? Which means that now there should be a second source of a non-linear realization. Let me call that of a BFD sector, where there's another U1 symmetry, which is broken down to Zm. Then that non-linear realized Zm is there all the way, then I can gauge it if I wish to. So this is important picture because now in addition to original PQ Patrick-Quinn scale, there must exist another scale which prepares non-linear realized Zm symmetry already so that I can gauge it when I wish to. Okay, so this will be important in understanding cosmic string spectrum. Good, so that's this part. And the third part, you might say, oh, I gauge now the shift symmetry. Is the notion of axion gone? No, the answer is no. There's a still good notion of axion local fluctuations. So if you were completely, the ideal model, like I completely gauge the entire U1, then it's an entire fluctuation, right? It turns into the gauge equilibrium. But here, starting with the axion fluctuations like that, I decide to gauge only Zm part, which corresponds to measure zero amount. So there's a good notion of local fluctuations everywhere. So I'm not losing axion yet. There is a good notion of axion, but the effect of this, therefore, will appear more in the axion string physics. So that's the thing that I want to discuss. So the question is, what happened to the axion string? So axion doesn't really feel the effect of this gauging. So what happened to the axion string? So that's the question. So this can be understood from the mixed tube anomaly analysis or alternatively breaking of the three group structures. But let me just use this one, simpler to talk about. So remember, axion string is a two-dimensional defect charged on the two form U1 symmetry. We talked about that a lot. And it is measured by this axion winding symmetry defect operator. Okay. So in terms of expressions, what this means is that let's say I had a string, axion string, cosine string. This is axion cosine string. And then there's a symmetry defect operator, which is non-trivial linking with that configuration. Right? So then this operation is that I'm measuring the charge of this object when there's non-trivial linking. So it spits out the U1 phase, which tells me what is the winding number of this configuration. Right? So if it has a winding number n, of course, I will learn that it has a winding number n. If it has 1, it has 1, and so on. Right? This is the like mathematical way of talking about measuring the charge of this object. Now, before gauging this subgroup, since everything is global symmetry, so here everything is a global background gauge field for global symmetry. And again, this is from the two-form symmetry. But remember, dA over 2 pi a was the current for U1 two-form symmetry, and I coupled that to its background gauge field. Now, I added one local counter term in such a way that everything is manifestly invariant under axion shift symmetry, because this combination is invariant. However, this thing is not anymore invariant under now a two-form transformation, because now if you just shift this by e lambda 2, this is not invariant. And this, of course, is manifestation of the fact that I do have a mixed phenomenon. What do I mean by that? If I turn on background gauge field of both electric symmetry and magnetic symmetry, in the presence of both background gauge field, that action is not invariant. That's the notion of a mixed phenomenon. Okay? And then if you care, anomaly inflection is basically this. Now, let me tell you the physics implication of that. So if I gauge Zm subgroup of Zk, again, previously it was anomaly among all the background gauge field, global symmetric background gauge field. Remember, that was two phenomena. Now, one of the things I've turned that into gauge field. And that was ABJ anomaly. Remember, ABJ anomaly is a testing, given a global symmetry, I'm testing whether it's good quantum symmetry. So two phenomena that turns into the ABJ type of anomaly. And now I have to figure out how much of the two-form symmetry remains to be still a good global symmetry. Something is broken. So that analysis can be done rather straightforwardly. So this is the symmetry defect operator for the two-form winding number symmetry. Now, if I decide to gauge Zm subgroup, which is like this gauge transformation, this symmetry operator is not gauge invariant. And of course, we are not allowed to use the gauge non-invariant symmetry operator to do anything. In other words, once I gauge this part, I have to figure out which amount of this two-form symmetry remains to be still good global symmetry. And obviously, under that shift, you can see that this is still a gauge invariant if alpha is m times 2 pi. Because the order of m from this shift is canceled by m from alpha. Which means that out of entire U1 two-form symmetry, which measures the string spectrum, only the ones with the alpha with the 2 pi n remains to be good global symmetry. Okay? So now, I'm ready to tell you the answer. So now let me do the Dirac experiment. I put some action string here, right? And then I'm measuring the winding number using good gauge invariant symmetry defect operator. If I do that, like I said, alpha always should be 2 pi m. That means that whenever I do, the phase is always now multiples of m. That is the only possible answer I can get out of this measurement. That means I will say as experimentalist that every action string has a winding number m times z. So pictorially, what that means is that before I gauge the subgroup, I had all integer valued action strings. The winding number take any integer value. As soon as I gauge it, what happened is that these Zm part are gone, only the m times z are surviving as a still action strings. Slightly it looks like it's a dramatic effect. However, if you think about it again, it's actually expected because if you had some fluctuations, right? And then if you decide to gauge it, you turn that into gauge degree of freedom. Therefore, you have to remove that from the physical spectrum. That's what basically is happening. Zm part, I gauged it. Therefore, that part should be now gauge degree of freedom. That's gone out of the spectrum. Then you can ask, are they going to complete it once and for all, or there are somewhere still? Right? So you can ask, what happened to other strings that are gone from here? The answer is that they are coming back as a BF string. Remember, in order to be able to gauge non-linear realized symmetry at all, I must have a second scale that realizes non-linear realized Zm to prepare the such a symmetry. So because of this fact, in the gauge theory, they are lifted up as a BF strings. So as soon as I gauge it, there is this dramatic shift of a string spectrum. And this survives as what's called the global strings, if you're familiar with the notion, which has the topological charges. And the other one converted from the global string into the local strings, what's called, or gauge degree freedom. Okay, so that's the picture. So with that, let me conclude. So I think that the non-trivial TQFT-coupling or topological modification of theory actually can lead to some interesting observable consequences. Okay, so here I haven't told you how easy it is to check all these string spectrums. So I'm telling you, in principle, there's modifications. And here, in understanding all those effects, generalized global symmetry is important important key tool. And I think this is just the beginning, meaning understanding phenomenological observable consequences of generalized symmetry. I think it had just begun, and there's lots to be understood. And I mentioned a little bit about the possible application to dark matter physics. And cosmic string seems to be modified a lot. There's several questions one can in principle ask and understand because of those TQFT couplings. You might ask, okay, how about the axion Yang-Mills or axion Q3? And we've been also working on this theory too, and it's much richer than what I told you today. There's many modifications one can do. I mentioned briefly about the non-invertible symmetry. Is there something with it? And then there's observable consequences. And I think I'm pretty positive about this. But with that, let me just thank you. And I'm sorry for running out of time. Running over time.
Thank you for the nice talk. Any question or comment? Any question from Zoom? I have one specific question.
Okay.
In your UV theory, UV completion, you after the integrate down fermion, you still have the kinetic term of B here, right?
Oh, you mean this?
Yeah.
Very good. Yes.
Then it still can be the TQFT in the low energy.
Very good. Good. So let me answer that question. So the question is, if I integrate out, looks like from a scalar term, erase from the scalar term, I get a BF action, BFT reaction. What happened to this? That's your question.
Yeah.
So what happened there is that if you derive in the IR equations of motion from B2 dB1, okay, including the term. So what you get is the equations of motion enforces B1 to be 0. So if you really settle down to that point, this becomes 0. So that's how you see the decoupling effect. I mean, I can tell you a little bit slowly offline, but basically, the once you get to the IR D by R, the consistency requires that this to be 0 by using equations of motion from the BF series.
Okay. Any other questions? Now let's thanks again. Thank you very much.
Thank you very much.
So we will have a seminar. So let me